graduate degree over years, sweat and trying to figure out how all this stuff works in the rare earth industry business. So I want to talk a little bit about the first part of that here today. I want to provide a little bit of perspective, first of all, because a lot of what you see in the rare earth sector these days is talking about new deposits and new discoveries. Oftentimes, you hear very low numbers, ppm ranges, sometimes 2-3%, sometimes 5%, sometimes 500 ppm. So you have to kind of look at what we're dealing with when we're talking about 14 lanthanide elements plus yttrium. Over that series, crustal abundance is on the order of about 220 ppm. That does include yttrium. So when you look at possibilities for potential deposits, you have to kind of look at it. What is it compared to in terms of crustal abundance? Now, the thing that you'll find with rare earths is that even though they're relatively high, 220 ppm is actually higher than gold, silver, lead, many other industrial metals. But even though the abundance is there, deposits are not. Very difficult to find occurrences where you actually have viable deposits, where you have enough concentration to think about doing any kind of upgrade producing rare earths. Additionally, you'll see that the concentration of these 14, 15 elements increases by about a factor of about 100 as you go up in molecular weight. Now, the other thing I should point out is that, I don't know how many of you here counted the number of cubes on the table. It's actually 17 up there. I don't know why they, promethium is shown because it doesn't occur naturally, so that's a non-starter. And scandium is also shown as a rare. But scandium actually rarely occurs in deposits for rare earths, so I don't really count that one as well. The other problem with the rare sector is lanthanum and cerium. Those are kind of the white elephants in the room because they, for all intents and purposes, compose about anywhere from 50 to 80% of the total rare earths. And that's usually in one or two minerals. So there's no way of selectively changing your operations on a mining or concentration endeavor to reject minerals that really don't have much value. You still have to go after minerals that contain these elements. So costs are involved. And if you don't take advantage of all of the rare earths that are available, then you're really leaving money on the table. So what are the fundamental requirements? You're looking for potentials that use processes that fit grade and mineralogy. And that's one of the things that oftentimes when people say they've got a rare earth deposit, all they'll tell you is that we've got picking up 2,000 ppm of RE or REO as it's often called. The problem is not really telling you what it is. Is it rare fluoride? Is it rare carbonate? What is it? Because that's important. We'll talk about it. You also have to have processes that are environmentally viable. Mining's come a long way over the last century and a half. And it's become this evil empire that back in the 50s and 60s, rightfully so, had problems. But if you look at mining operations these days, they're actually quite responsible in what they do. But it still has to be factored into what the deposit potential occurrence tells you must be done there. And then it has to be economic. You have to look at it and say, all right, does this really make sense from an economic perspective? Because if you can't make money, why bother? And with that, what is the definition of an economic resource? Essentially, it's very simple. It's just a deposit that can be worked at a profit under existing economic conditions. What's the other problem with rare earths? Over the last 40 years, prices are actually very, very volatile. A lot of that has to do with supply and demand, changing technologies. It also has to do with who controls the vast amount of rare earths that are coming from the ground. With that, you see that China is in control. So much like CBMM has a niobium deposit down in Brazil, it is such an easy process to make the, I should say, easy mining operation, really what it is. And it's a vast deposit, so they can actually control the prices of niobium from the fact that it's easy for them to either increase production or decrease production. Makes it difficult for other people that want to come in and try to get into the niobium market because the prices drop. Maybe you can't make money. That's what happens in rare earths. So there's a lot of factors that that control the fact whether occurrence may be viable. Excuse me. Geology, mineralogy, grades, research. I mean, those are the biggies. Which then dictates, in most cases, the mining methods that you must use, and then also the metallurgy in terms of beneficiation and extractive sides of the equations. So I'll be talking about extraction energy, because I think it's important, very important on the rare earth side. Resource considerations. Location is a big one, right? Unfortunately, in terms of finding minerals, they're not always ideally located. We'd like to be able to drive 5 minutes to our job at the mine from here in Golden, but that's not always in the best wishes of everybody else in your neighborhood, right? The location is important. That's also difficult when your occurrence may be out in the middle of the Gobi Desert or something like that. So oftentimes we're faced with location as being a big question mark. Where do we have to do this? Because not only do we have to look at our neighbors, how we affect them, the societal factors are a big deal these days. But you also have to look, how do we get there? Where do we get the people to work the property? Where do we get reagents? Where do we get equipment? So there's a lot of things that location really, really is important in terms of is this going to be viable? Geology is also very constrained by how deep is the deposit. If you've got a low grade source, you have to spend a lot of money to get down to depth. It may not be economic to do. Geometry. If you look at Mountain Pass, it actually was a outcropping of carbonatite site that was on the surface, but it was tabular in form, and it dove at about 45 degrees angle down into the earth. So the problem with Mountain Pass is that as they mine more, stripping costs go up. So geometry is also a big. And then are you chasing a fairly large, contiguous type of deposit, or are you chasing veins? It may be high grade, but if I have to mine small areas and chase them around, my mining cost may go up. And of course, overall, you have to have enough to justify the investment. The other issues that come into play is that you have to look at the deposits where it's been weathered. An example of that is Mount Weldon in Australia had been a monazite deposit at its very beginning, but over the eons, probably was a tropical environment, and through a lot of weathering, rain events, you saw that monazite become altered to a degree that is no longer a true monazite. It's a supergene. Some of you may have heard talk yesterday about carbonatite. That's exactly what happened. Not well. It is a supergene and therefore fine grain, makes it more difficult to deal with in terms of economic recovery. Other associated minerals. What's there along with your potential? There, typically in carbonatite, you're going to have a lot of carbonate. These processes to extract the rare earths require acid, so you need to get rid of. So you have to look at both what's valuable and what's waste. Sometimes you have deposits that have other byproducts that may be valuable. You look at monazites that are now coming back into vogue in terms of sources for rare earths. You see that monazite is actually a very good alternative to bastite. It tends to be higher in neon, prazio, as well as heavies. However, it typically has thorium with it. And you find these deposits, heavy mineral sand deposits, where when you have zircon or rutile, and monazite for decades was the stepchild that they had to get rid of because of the radioactive content. People are now going back and looking for waste piles and saying, well, that's a source of rare earths. Data for all of the geologies usually derived from multiple sampling methods and forms. You might be core drilling, you may be going digging sample dishes, a lot of different ways. You have to make sure that there's a lot of sampling that's done. So let's talk about minerals a little bit. Bastite is one of the biggest ones you'll find talked about. It is a rare earth fluorocarbonate. It is what they call a light rare earth, which means that it's primarily lanthanum and cerium with minor amounts of heavy. There's a fair amount of neo and prazio, but it varies from deposit to deposit. Next in line is monazite. Again, it's a light lanthanide, but it tends to be higher in neo and prazio and heavies. It does have the thorium component, which has always made it difficult, very difficult to bring online because now you have a radiation that can handle the waste materials that result from the thorium and uranium is typically involved there. And then you have ion absorption plates. Typically they're higher neo, prazio, and heavy. And they're actually very low in some of the lights. However, they're unlike the bastite monazite, they're actually very low in terms of overall total concentration of rare earth, usually on the order of about 0.5%. Then there's xenotime, which is essentially an yttrium enriched monazite. Typically, it's very high in yttrium, may have a little bit of cerium, may have a little bit of neo and prazio, but typically it's going to be an yttrium source. And then this guy, there's a lot of eudialyte. You may have heard about deposits up in Greenland. But anybody that's familiar with chemistry can look at that particular mineral and say, what am I going to do with all of this? got lanthanum, cerium, heavies, niobium. Who knows what the real composition is? Then there's that little thing called silica. Anybody that's ever had to deal with silica gels in a process knows that that is a very difficult hill to climb in terms of trying to process this mineral. Even though it's rich in what we want, it's not necessarily meeting the requirements needed to produce the rare earths. The other thing that's interesting is that we already touched on is that the Achilles heel for these minerals is that you've got typically 1, 2, maybe 3 different minerals, but you're dealing with multiple elements. So costs for mining, for separating, purifying, all go in. If you into treating the few number of minerals, and therefore your costs typically are going to be elevated due to the fact that so many separations have to be made. So if you can't sell all of the elements, then the few will have to bear those costs. So mineralogy is really a close look at these mineral species. It's taking microscopic looks at what does the mineral look like. You're looking at crystal structure, matrices, all these things that define what the mineral really is. And you have to look at it because sometimes you may analyze for rare earths. They may not be able to be concentrated or chemically attacked because you can't get to them if they're locked in with other minerals. Grain sizes are very important. When it comes to beneficiation, grain size is your friend. If it gets to be too fine, then you have a very, very difficult time making concentrate to get rid of gangue material. In our crystalline growth, I mentioned that before, that affects the concentrate that you can make. And then, of course, the gangue material. What is there? What do I have to worry about? Sometimes if you have a relatively benign mineral that's attached to the grains, like barite, that typically is fairly inert in any kind of chemical processing for rare earths, that may be okay. But if you have a lot of calcite, lead, uranium, those materials that are attacked by acid because rare earths in solution also go into acid. Now you have further separation. So this is usually done at a microscopic level. Gives you a great idea of what all of these different properties look like. And when you hear people talk about potential rare earth sources, too often a lot of this stuff is never mentioned. How many times do you say, well, you know, Joe Blow's got this new source that's going to save the world for our rare earth needs? They never talk about these details, like what type of mineral it is, what types of properties they have. It's very hard to get that information off because it is very important. So it's better to ignore it rather than come out and say, well, you know, I got monazite or I've got ionic clays. Two different things. So it's a lot of times it just goes unspoken. And worse, a lot of people don't know to ask the question, what kind of mineral are you dealing with? Because if you don't know, you don't have a good feel for where you might do in terms of potential problems. Metallurgy side of things, we're talking about beneficiation. Liberate and separate. You got a rock with rare earths in it, minerals, you're going to have to liberate those different grains It usually involves crushing, grinding. That's expensive. Usually a lot of electricity is expended in terms of just liberation. The by far the largest cost on the mining and beneficiation side of things. But you're still at this point concentrating compounds. Talked about that being a fluorocarbon, monazite being a phosphate material. These are still in the compound form. So then you get into extractability. How do I extract the rare earths from these compounds? So really what we're talking about, how do you get the metals from the compound? Not necessarily as a metal, it could be just putting it in a solution. You have to extract them from compounds. And it may be direct, it may be indirect. So primary cost, look at this a little bit. Grade is an inverse function of mining cost. Lower the grade, the higher your mining cost. To get X pounds of or tons of rare earths, it takes more and more material being mined, lower the grade. It's common math to determine. It also may involve the mining method. You know, you're going to have to go underground for a low grade. That could be a difficult problem to figure out. Crushing and grinding, you're liberating mineral species. Again, that's an inverse cost of grade. More tons that you have to run through a crushing and grinding circuit, you need more wear, larger equipment. So costs go up with lower grade. Grain sizes, again, that's on the beneficiation side. It means you have to crush in smaller sizes to get individual mineral grains of your valuable minerals. Rock hardness, there's a lot of silicates involved. So it's typically a lot harder to crush and liberate these mineral grains. So therefore, wear costs go up. So we're trying to, within beneficiation, we're trying to separate the valuable minerals, compounds, again, from the gangue. Most often this is flotation. Widely used everywhere. It can be very, very, very effective. But in terms of the rare earths versus sulfide types of deposits, finding collectors that attach to the mineral surfaces that you want to float can be difficult. In fact, CMI has been involved with a number of projects trying to find and improve collectors to make this process more effective and therefore make lower grade deposits more viable. So again, many factors can affect these costs from the beneficiation all the way back up to the mining. And then you have extraction. And here's where I'd like to make the point that the mineral compound, whether it be a fluorocarbonate, phosphate, or even the case of eudialyte, which we don't really know what that is, it matters. And I like to look at it from the standpoint of how much energy does it take to release rares from those compounds. Because that affects, again, what you can tolerate in terms of grade for potential occurrence. So there's a very, maybe a familiar type of extraction process, like the blast furnace, where it's essentially a direct reduction of iron from iron ore concentrates in a blast furnace. It's a lot of energy, but it's also very effective. It is cost effective. So that's an example of very high energy extraction. You know, we're actually melting things to reduce the iron into a molten state. So the rare earth compounds are actually very similar. It takes a lot of energy to release rares from fluorocarbonates and from monomers, because rare earth fluorides are very stable as a compound. Same thing with rare earth phosphates. They do not go into solution easily. Like to say, you have to basically take a hammer to it to get the materials to go into solution. So these are typically associated with commodities. We talked about that a little bit. They're very stable, and it takes a lot of energy to get the elements extracted. So what does that really mean? It means that you have to have acid bases, usually elevated temperatures, accomplish these to get materials to go into solution. Again, if you have high percentage concentrates of rare earths, it's fairly easy to use acid bases, temperatures to your advantage, because you've rejected a lot of these gang materials that would also be affected by these methods. And if you don't, now your cost will is reagent cost will up. The other part of it is then you also have fluorides and phosphates that also become extracted, and they can be problematic. In the case of basticides, it's one of the typical processes why they use in China is to use a sulfuric acid base. And what that does is essentially drive fluorine from the process as HF. If anybody has used HF in a process, you know it's very corrosive. It tends to be problematic from an equipment standpoint. And if it escapes the atmosphere, then it really does become a problem. So an example of a low energy extraction would be a rare earth ionic clay. They're born of highly weathered strata. May have been a fluorocarbonate, may have been a monazite at one time. Usually found in hot, wet climates, subjected to a lot of heat, precipitation. You get acids form as the minerals degrade, mineral structure is lost, and you can actually get these rare earths that go into solution and the overall mineral structure completely degrades, and you end up making supergenes, which then can further progress into these ionic clays, which you just basically have fine silicas of alumina clay materials, and you have rare earths that are attached to the surface of these particles. And what you see is that the rare earth elements have adsorbed to the clay surface. They're typically very low grade, maybe 0.5% less, but the extraction is eventually solution mining. Ammonium sulfate will remove rare earth from the surfaces of these ionic particles, from the clay particles, and puts rare earths into solution, and easy. It's actually fairly cheap as well. So, pop quiz. You know you're going to be set. You're going to get a quiz today, but here we go. If I give you a choice of 5,000 ppm rare deposit, and you have to choose either an ionic clay or a basticite deposit, or it doesn't matter, you just need to build a bunch of Teslas, doesn't matter how we get it. Which would you choose? Ionic clay or basticite for processing extract? Anybody choose basticite? Okay, we got somebody that would. How about ionic clay? Most people would go the ionic clay because of the fact that you can use relatively simple solution mining to remove the rare earths and get them into solution, and recover them at relatively high recovery rates. It's a little bit questionable there because we are dealing with clays and how you managed to get good permeability within clay deposits. Sometimes up for debate. Positives are that in situ mining is low capital, easy to set up, low operating costs from the reagent standpoint. Negatives, questionable recovery. It's not particularly eco-friendly. You're drilling holes into the deposit themselves, injecting ammonium sulfate solution, which you have to collect, and then process from there. So what happens to these deposits after you've done this? How do you wash the resulting residues from these chemicals? So it's not the most environmentally friendly process. Pesticide kind of loses on all kinds of little sorry, it's in situ mining is basically impossible because if you have other materials along there that will solubilize in high acid environments, because that's really the only way you can mobilize the rares at this point. It's very difficult to get the material into solution and utilize heat. So essentially the reagent costs are prohibitive.
I have a question.
Sure.
With the ionic clays, do they stratify into layers so that you would have impermeable upper and lower boundaries for doing in situ mining, like happens with uranium, or is it just varied?
I think it's very like it's like anything. You can find different. Yeah, it depends. It's described as a chromatographic type of deposit because you have these rares put into solution and they can migrate as they're being washed. So you'll find that different elements will congregate in certain areas. So it's possible that other parts of the deposit may be high in cerium and lanthanum, but nobody cares about. So they're always looking. But yes, they could be confined in ways. You know, geology is a funny thing; it's never consistent. So the other thing is that if you decide you have to mine this material, look at the difference, the amount of polys that you would have to produce an equivalent amount of rare material. 17 times that of Mountain Pass, which is essentially at 85,000 ppm, consistent numbers. The other thing that's difficult is the fact that concentrating minerals from a very low overall level of mineral content is to remove the gang material, you have to have more specific technology in terms of collectors. And that's, again, another area where CMI has been very active. How do I come up with a collector that's very specific for bastosite or monazite, whatever you're looking for, to allow you to selectively pick these different minerals from all of the other gang materials. Because without sufficient concentrate grade, your reagent costs would be again prohibitive. So in the end, grade matters, always does in mining. It's just that when it comes to crustal abundance of 220 ppm, 500,000 ppm just doesn't look that attractive. When you have other areas where it can be 80,000 ppm or above. They're just hard to justify. Unless the extraction is low energy. That's why the ionic clays have an upper hand in terms of producing a lot of the heavies, is that they are very low energy, it's easy to recover the materials, and impurities don't interfere. Problem is, how do you safeguard environmental questions that arise by injecting fluids into the earth. That's the Achilles heel for item plays. High energy extractions, you still need these mineral processing steps. You have to reject the gang. You try to concentrate the valuable materials and reduce mass. So if you look at relative numbers, Mountain Pass, 8.5 TREO, our ore body mix concentrates in the range of 65% TREO concentrate. Bear Lodge is another example up in Wyoming. They're in the range of 2 to 6%. It's a more complex ore body. It's also been weathered. Don't have good numbers of what they project for concentrate there, but at least at that level of initial concentration in the ore body, there's a chance. And then in the US, monazite is coming into play in terms of interest. And when coupled with heavy mineral sand production, which is monazite is the byproduct, you can get a 55% total REO concentrate. By comparison, if you start with something that's 500 ppm TREO, and typically in today's technology in terms of ability to concentrate from ore to the highest level possible, it's usually 8 times is a good rule of thumb. So if you start at 500 ppm, you might get a 0.4% concentrate. So that's not particularly enticing. So you kind of wrap this up. If you're looking at resources versus Occurrence, it all boils down to economics. You're not going to do anything if you can't make money, right? So can is high grade deposit preferential to low grade? Typically, yes. And no. It depends upon what you're dealing with. If it's ionic clay, it could be preferential. But if it's a high energy type of mineral, then no, it won't. Mineralogy is important. Again, it's just a rehash of the fact that you've got to get you have to know how the valuable minerals are locked up in the actual morphology of the deposit. Geology is important, depth of occurrence, all these different. So this particular slide is one that talks about potential deposits versus actual operation. And if I remember right, the red are essentially rare ore deposits scattered around the globe. Blue triangles are monazites, fine. And then the blue circles basically show where you've got operating facilities, and green, the green are the separations and production facilities in a few areas. So you can see from this particular map, there's plenty of potential. So the question is, why don't you see more of the blue and ellipses and green circles? A lot of it has to do with what we've been talking about. What does it take to get these particular occurrences into a state where you can economically gain value?